All right, so we are now starting Unit 12, which is Chemical Kinetics. Chemical Kinetics is one of the big 5 tested on the AP exam, and a lot of people think it's really hard. We do not. We do very well with this section, but it takes time and energy, not time and energy to do the stuff that you should have turned in this morning. So I'm fairly sure that you've taken physics or are in the process and you know what kinematics is. What is that?
The study of motion.
The study of motion. So we're going to talk about chemical kinetics, which is kind of like kinematics. And it's the study of the speed with which the reactants are converted to products, otherwise known as the reaction rate. You know that any rate at all is the change in something, and I don't care what it is, over the change in some unit of time. All right, so in chemistry, if you have a reaction that A is converted to B, the reaction rate would be the change, the concentration at time 2 minus the concentration at time 1 divided by the elapsed time. All right, if you boil that down, it would be this. Rate is equal to the change in concentration over the change in time. Here is a little aside for you. Those brackets denote concentration in molarity. All right, let's look at this graph. This is for this reaction, 2NO2 is decomposing into 2NO plus O2, and we have graphed concentration on the y-axis and time on the x-axis. At time equals 0, we have all the concentration is due to the reactants. There are no products. As time goes on, more of the reactant decomposes while the product forms. All right, so to measure the rate of this, you could either measure the disappearance of the reactants or measure the appearance of the products. Now, the reaction rate is proportional with regard to stoichiometry. If you look at the stoichiometry of this reaction, for every 2 moles of NO2 that are formed, you have 2 moles of NO and 1 mole of O2. So if you would look at this, there's always twice as much NO formed as O2. Another way to look at this is the rate of decomposition of NO2. So would be equal to the rate of disappearance of NO2 is equal to the rate of appearance of NO, and it is 2 times the rate of appearance of O2. Now, if you were talking about the instant rate of speed, and you had a graph, how would you find the instantaneous rate of speed?
The slope.
Slope of a line tangent. If I wanted to know the concentration at time, I don't care, I would draw a line tangent to it, and we will pretend that is tangent. Everybody leave me alone. And then we would take the slope of that. Yep, you could also do that, all that fun stuff. All right, if you were driving a car, what would where would you look for your instantaneous rate of speed?
Speedometer.
The speedometer. Okay, so the instantaneous would be the point in time. If you were to look at your average speed, how would you do that? Your average speed is miles per total distance divided by total time. Okay, if you wanted to know your rate here, it would be divided by time. All right, we need to talk about the factors that will affect the rate of reaction. All right, number 1, the nature of the reactants. If you took solid potassium sulfate and solid barium nitrate and forced them together, you would get no reaction. However, if you took some time to put them into an aqueous solution, then they would react. Because if it was an aqueous solution, you would have floating around and they would be able to find each other. Okay, so the physical state matters, as does the chemical identity. I think you could see when something is ionized, they have another pressure, another force affecting the rate of reaction. That would be the electrostatic force that comes from the attraction of opposite charges. So ions of opposite charge are going to react really quickly because they have that push from electrostatic force. Let's talk about some other things. Usually, you do recall that as a reaction happens, the first thing that has to happen is bonds must break in the reactants in order for new bonds to form in the products. If you have a lot of bonds in the reactants, it's going to take a long time to break them, and therefore it would be a slower reaction rate. Okay. Something that has strong bonds, something that has a large bond energy. This would have a large bond energy because that triple bond is pretty massive. It's going to react more slowly because it's going to take a lot of energy to break that. Okay, another thing that will affect the reaction rate is the concentration of the reactants. The more reactants you have, the more molecules, the more collisions that will occur and actually bring the the reactants together to react. Temperature. The slang term is heat 'em up and speed 'em up. The faster they move, the more likely they are to come in contact into each other, and therefore they're more likely to react. All right, as you increase temperature, you have more collisions that have the needed activation energy. This is the first time you have encountered this term. Circle it because it's very important to kinetics. Activation energy is a minimum energy required to react. Why do you think a reaction has a minimum energy needed to react? Tell me.
Less than the current state.
What are you using that energy for?
To break the bonds.
To break the bonds to
Start the reaction.
start the reaction. All right. Here it is, the answer to every AP question on the planet. The Maxwell-Boltzmann curve. What is this, 47 times we've talked about the Maxwell-Boltzmann curve? I expect you, when you take the AP exam, to come to me afterwards and say, I used it 47 times. Once would be sufficient. Okay, let's look at this. These are the fraction of molecules, and this is kinetic energy. So let's say this is temperature 1. And this is temperature 2. Temperature 1 is less than temperature 2. This is the activation energy. So here we go, kinetic energy. If you look at this, as we have increased the temperature from temperature 1 to temperature 2, we've moved this over to the right, and there are more particles that have the requisite energy to react. Now, you can do some really nasty math. Here's the really nasty math to prove the Maxwell-Boltzmann curve, or you could just say the curve is shifted to the right, which means that there are more particles that have the minimum energy needed for reaction. F is the fraction or the frequency of particles. E is the natural analog. EA is the activation energy. R is the big boy gas law constant. And T is the temperature in Kelvin. My guess is You need to be able to talk about the frequency of particles. You might, if you know the gods are not smiling on you, have to solve this, but I don't really think so. I think what we just talked about would be sufficient. Okay. Now, I'm sorry that this got dropped on the floor. And I'm also sorry that this got rolled over to the next page, because this is a nice supposition. A general rule of thumb that you can use is that a 10 C increase in temperature will double a reaction rate. That might come in handy on a multiple choice question. All right. Another thing that we'll talk about is the surface area of a reactant. The exposed surfaces will affect the speed with which a reaction occurs. Here is a cube of some reactant. All right, we'll call it reactant 1, and it needs to react with reactant 2 in order to make a product. If it is has a small surface area, that means it's a big piece. There are very few surfaces that R2 can attack or collide in order to force a collision to make a product. If you were to increase the surface area, make the particles smaller, there would be more places for R2 to collide with R1. Does anybody know what a grain silo is? Right, it's a large cylindrical storage facility, generally for corn. So like if you were a dairy farmer, you would either raise the corn or buy the corn, put it into a silo, and then feed your cattle over the winter. Well, the way they fill a grain silo is they conveyor up the pieces of corn. It's generally off the husk. And it goes to the very top and then drops down to the bottom. Well, when it's dropping down, because of the potential energy of being at the top of the silo, it hits the other particles with a great deal of force, making dust particles of corn. Have you ever seen corn dust?
Do we want to?
You probably have seen corn dust. Cornstarch? Yep. Cornstarch. Okay, cornstarch would be a hydrocarbon. When you have a very large surface area, little itsy bitsy pieces of corn, and you add oxygen to it, you can have what kind of reaction?
Redox.
Hydrocarbon plus oxygen. Combustion, a combustion reaction. And sometimes they've gotten better at preventing that. But in the olden days, there would just be huge explosions that would kill people. From corn silos. Yeah. The same thing with coal dust.
What a way to die.
Mm-hmm. Yeah, what a way to die.
Death by corn explosion.
Yes. All right, now this is all part, oh, you know what? I forgot number 5, big time, and it's a really important thing. The other thing that can affect the speed of a reaction is a catalyst. A catalyst is a substance that lowers the activation energy but is not changed in the reaction. All right, I'm certain that you've all taken bio and you talked about catalysts in biological systems, yes? All right, and I think it is something that's in the reaction that goes in and out looking exactly the same. It is just there to lower the activation energy. All right, we'll talk about that a little more. All right, so the collision theory is important. That's what all of this stuff is. The first tenet of the collision theory is that molecules must collide in order to react. If they don't hit each other, then they can't react. You could have all the activation energy in the world, and if they're not colliding, they're not going to react. The second thing is they have to collide with sufficient energy. That energy is the activation energy, and they must collide with the correct orientation as well. All right, so here is a graph of the potential energy. The x-axis is called a lot of things. I generally call it a coordinate, a reaction coordinate. All right, so the reactants possess a certain amount of energy due to the bonds within them, and the products will have a certain amount of energy due to the bonds between them. In order to go from the reactants to the product, you must have the minimum energy needed to react. That is activation energy. Activation energy is always equal to, this place right here is called the transition state. Another word for it is the activated complex. I like transition state. I think it's more universally used. All right. So the activation energy would be the energy of the transition state minus the energy of the reactants. Another way to look at that is always here, from the reactants to the apex. Okay. Now this speaks to the way that molecules must be oriented in order to react. It could be that these two molecules must be lined up so that this forms a bond with these two. So the little white circle needs to then be here, and maybe these guys are set free or bond with this. If it doesn't hit just like this, you won't have a reaction. So the orientation must be correct. Now you can see that there are probably lots and lots of collisions that occur that do not result in product being formed. In this case, in this scenario, 1 out of 4 orientations will cause a reaction. All right, so to go back, activation energy is the minimum energy required to cause a reaction. Excuse me. It comes from the kinetic energies of the colliding molecules. The kinetic energy in a collision is used to stretch, bend, and ultimately break the bonds that allows a chemical reaction to occur. The value of the activation energy varies from reaction to reaction. Each reaction has its own activation energy. These should be your friends because you're going to see these for the rest of your chemical life. So here is an endothermic reaction. We have energy on the X, the reaction progress on the Y. I need to hearken back to something from thermodynamics. What do you call the energy of reaction?
The entropy.
The enthalpy. The heat of reaction is equal to the energy of the products minus the reactants. That doesn't change. Didn't lie. Here it is right here. The energy of the reaction. So when we talk about this endothermic reaction, which you should think of as a step up, okay, that means that the reactants have lower energy than the products. When we look at this, we can measure two different types of energy, the energy of the reaction and the activation energy. Remember, the activation energy is always the energy difference between the reactants and the transition state. This would be an exothermic reaction. And it will be, delta H will still be the products minus the reactants. And the activation energy is still the difference between the transition state and the energy of the reactants. So if we look at this way, we see that this is the energy of activation energy. Let's say we would like to see the reverse reaction occur from here to here. The energy, activation energy would be, this time this would be the reactancy of the product, from here to here. Get that? All right, so somebody way smarter than us, Mr. Arrhenius. Actually, I've never heard his name spoken out loud, so that's my take on how to pronounce it. Could be wrong. He found a way to marry the collision model and reaction rate. As you may guess, it's kind of nasty with derivations in a big equation. But it talks about the fraction of molecules that have the requisite activation energy, the number of collisions that are happening per second, and the fraction of the molecules with correct orientation. All of these things are necessary for reaction. So he made this rate constant that you will be very involved with tomorrow. And he says the rate constant is equal to the activation energy, is equal to the frequency of collisions raised to the activation energy over RT. All right, what I want you to get out of this is this big, huge thing. And you may not even need the equation to do this. If you have a high activation energy, that means you have a hill that's quite high. The rate goes down because it takes a longer time to climb the hill. Okay? If you look at this, as the temperature goes up, the rate goes up. All right, tricky math, tricky math, tricky math. Here it is. This is the part you want to know. This allows you to calculate the activation energies from two known temperatures when we're talking about K. Remember, K is the rate constant. I'm going to do a pen cast of a couple of these, and then I think that's all you need to know from me.
The derivative of the frequency is temperature? Or, I thought it was useful. How do you get 1 over 2?
Where?
Number 5.
I don't know. All of a sudden, magic occurs. The only thing that I really is if you do this, the slope is EA. That's kind of all I care about. And I don't think you should care about it much at all.